Hello viewers, welcome to the lecture series on alkyl halides. In the present lecture, we will talk about the reactions of alkyl halides. But before starting that, let's recapitulate what has already been dealt about the alkyl halides. So, we've already talked about the importance of alkyl halides in everyday life, then about their nomenclature, the physical properties of alkyl halides, and also the various methods of preparation of alkyl halides. In the present lecture, we would be talking about the reactions of alkyl halides, but before we start on the reactions of alkyl halides, it is better to recall the structure of alkyl halides and also recall some of the important terms which will be used during the study of the reactions. So, the reactions of alkyl halides are many, but in the present lecture we will talk about mainly the substitution reactions and the two types of mechanisms involved, that is SN2 mechanism and SN1 mechanism. At the end of the lecture, we would be summing up what all has been dealt in this lecture. So, we start with the recall on the structure of alkyl halides. As you can see, the alkyl halides have a structure where the halogen atom is bonded to a sp3 hybridized carbon atom, and the halogen being more electronegative than carbon, there is a bond polarity of the CX bond, and the carbon atom has a partial positive charge, whereas the halogen atom, which is more electronegative, has a partial negative charge. And as we proceed in the lecture, we would realize that a number of reactions go by the polarity of this bond. And before we start the reactions of alkyl halides, let us recall some of the very important terms which we will be very often using during the discussion. So, leaving group is the one that is displaced by the nucleophile during the reaction. Some of the examples are iodide, bromide, chloride, tosylate, mesylate, water and ammonia. A substrate is the compound on which the reagent acts, and a reagent is the species which reacts with the substrate. So, if we look into this reaction, we would see that the Rx, that is an alkyl halide, is the substrate, wherein the X or the halogen atom is the leaving group. The hydroxide ion, which is used during the reaction, is the reagent, or in this particular case a nucleophile. So, what is a nucleophile? Nucleophile is the species that donate electrons, that is, they are electron rich. Therefore, they seek electron deficient centers, and generally they are Lewis bases. They are the negative ions or neutral molecules with lone pair of electrons. Some of the examples with negative ions are hydroxide, methoxide, amide, and the ones with lone pair are water molecule and ammonia. So, when we start with the reactions of alkyl halides, we start with substitution, though the alkyl halides show elimination reactions and reduction and also many other reactions. So, we start with the substitution reaction. In a substitution reaction, one species replaces another, and in case of alkyl halides, the halogen atom in Rx is replaced by another group or atom, for example, a hydroxyl group. As is clear in this particular reaction, the alkyl halide gets converted into alcohol and the leaving group, that is the halide ion, leaves from the substrate. The nucleophilic substitutions in particular are the substitution reactions where the reagent is a nucleophile. These reactions are typical reactions of alkyl halides, and in presence of a nucleophile, the nucleophile replaces the halogen atom and the halogen atom leaves as the halide ion. An example of a nucleophilic substitution reaction in alkyl halides is ethyl bromide reacts with the hydroxide ion and gives ethanol and bromide ion. So, for nucleophilic substitutions, the halide ion is very weak base and releases a proton to other bases. Besides that, the alkyl halide readily loses the carbon to other bases, and the weakly basic halide ion is a very good leaving group. All these factors favor for substitution reaction in alkyl halides. The substitution may take place in two ways in case of alkyl halides. In the first case, the nucleophile attacks the electrophilic carbon and replaces the halide ion simultaneously. The CX bond breaks heterolytically, the nucleophile attacks the carbon atom and simultaneously the nucleophile gets attached to the carbon, the halide ion leaves. So, this is one way of the nucleophilic substitution in alkyl halides. In another case, the CX bond breaks first and then the nucleophile gets attached to the positively charged carbon atom. If you look into this general reaction, we see that the CX bond heterolytically again breaks and gives a carbocation and the halide ion. This carbocation in the next step gets attacked by a nucleophile and hence gets substituted to this particular carbon. The two mechanisms have been named as SN2 and SN1, and the mechanism is established by the kinetic studies of the reactions. Also, the mechanism depends on the following factors: the nature of the substrate used, reactivity and concentration of nucleophile, nature of leaving group, and the nature of solvent. The first mechanism which we will discuss is the SN2 mechanism. SN2 mechanism is called substitution nucleophilic bimolecular, and we shall see why it is called like this. Consider the reaction of methyl bromide with a strong nucleophile like hydroxide ion. Methyl bromide reacts with hydroxide ion to give methanol and bromide ion leaves. The hydroxide ion replaces the bromide ion in this reaction and a primary alcohol is formed as the product. Now, consider the kinetics of the reaction. You would recall that a rate equation is rate is equal to the rate constant, the concentration of the alkyl halide in this particular case, and the concentration of the nucleophile. Reaction of alkyl halides, rate depends on the concentration of two species, especially for the SN2 mechanism. So, the rate will be equal to K, the concentration of methyl bromide and the concentration of the nucleophile hydroxide in this particular case. The rate depends on the concentration of methyl bromide and hydroxide ion, and therefore, this particular reaction from the kinetics point of view is a second order reaction. Therefore, we call it an SN2 mechanism. So, S stands for substitution, N for nucleophilic, and 2 stands for biomolecular because it depends upon the concentration of the two species involved. The SN2 mechanism has been substantiated by the experimental facts. It has been found that rate of the reaction is dependent on the concentration of the alkyl halides and the nucleophile. The rate of the reaction with a given nucleophile decreases with increasing size of alkyl halide. In the substitution of a chiral alkyl halide, an inversion of configuration is observed. The SN2 mechanism, if we look into the details of this, it is a one-step mechanism, or we can say that it is a concerted mechanism. The attack of the nucleophile and removal of the leaving group is simultaneous. As you look into this equation, you will realize that this methyl bromide is attacked by the nucleophile, that is hydroxide ion, and via the formation of this transition state, it leads to the formation of the alcohol, and the leaving group leaves, of course. And it is noticed that with the progress of the reaction, the hydroxide carbon bond strengthens and the carbon halogen bond weakens. So, if we look into the transition state in SN2 mechanism, we will notice that the carbon which was previously sp3 hybridized in the alkyl halide and was tetrahedral in nature gets changed into a sp2 hybridized with a trigonal planar shape. It means that the transition state is actually planar, and the carbon atom to which the nucleophile and the leaving group are attached is pentavalent. The dotted lines in this particular transition state, as you can see, these two dotted lines, these depict the partially forming bond, and this is the partially breaking of the bond. So, this is the transition state of the SN2 mechanism. The nucleophile and the alkyl halide combine to form a pentacoordinate transition state, as you can see in this particular reaction, and this happens to be the rate determining step which involves both the alkyl halide and the nucleophile. The pentacoordinate transition state dissociates to form the product in the next stage, that is the substituted alkyl product we get. Just look into the energy profile of a SN2 reaction. We will notice that in the reaction coordinate, the transition state has the highest energy state and the reactants are at the lower energy state as compared to the transition state, but the product happens to be at the lowest energy state. Therefore, the reaction is favored in the forward direction. So, you can see that this is the transition state. As far as the stereochemistry of SN2 mechanism is concerned, attack of nucleophile is from the side opposite to that of the leaving group. Therefore, the configuration of carbon inverts like turning inside out of an umbrella under a strong wind. As you can see, when the nucleophile approaches the carbon, just the inversion of the configuration takes place. The groups which were on this side of the carbon atom were there, they all get to the other side. As a result, from a R configuration we get a S configuration. So, inversion of configuration is observed, and on the name of the scientist who invented it, it is called as Walden inversion. If we look into the similar kind of reaction, here again it is a butyl bromide. It is a chiral molecule which has R configuration, and this is getting converted into S configuration after the SN2 reaction. The inversion of configuration indicates the existence of transition state also. Now, the alkyl halide substitution takes place by SN1 mechanism also. SN1 stands for substitution nucleophilic unimolecular, and we shall see why it is called so. Consider the nucleophilic substitution reaction between a tertiary alkyl halide with water. Similar to the SN2 reactions, there is formation of a tertiary alcohol with the release of a hydrogen halide molecule. Now consider the kinetics of this reaction. For the particular reaction in case of SN1 mechanism, the rate depends on the concentration of only one species. So, we can write the rate equation as equal to K and concentration of the tertiary alkyl halide. The rate depends only on the concentration of alkyl halide, therefore, we call it a first order reaction, and this justifies the name SN1. S stands for substitution, N for nucleophilic, and 1 is for the unimolecular reaction. The experimental facts substantiate the SN1 mechanism, and it has been observed that doubling of substrate concentration doubles the rate of a SN1 reaction. The rate of the reaction is favored by the bulkiness of the alkyl substituent. In the substitution of a chiral alkyl halide, a racemic mixture of products is obtained that will be justified when we look into the exact mechanism of this substitution reaction. So, the SN1 mechanism follows two steps. In the first step, heterolytic cleavage of CX bond leads to the formation of carbocation, and here the rate depends on the stability of the carbocation which is formed. This step of SN1 mechanism is actually the slow or the rate determining step, and it is the step which is energy consuming, therefore, it moves slow. In case of SN1 mechanism, there are two transition states actually. This is the transition state just before the formation of the carbocation is when the CCl bond is largely broken and the cation is beginning to form. So, as you can see that this is delta plus, delta negative, this is the bond which is partially getting broken and Cl is trying to leave as the leaving group. The carbocations which are formed during an SN1 reaction are obviously positively charged in nature. These are planar and are sp2 hybridized. So, we shall see what is the significance of this positively charged planar carbon atom, and these carbocations are very reactive intermediates. And as far as the order of stability and reactivity goes, the tertiary carbocations are stronger as compared to the secondary ones, which are less stable than primary, and finally, the methyl carbocations are the least stable, and in fact, the reactivities of carbocations match their stability also. So, the tertiary carbocations are the most reactive by and follow SN1 mechanism, then the secondary, the primary, and finally, the methyl carbocations do not show any SN1 mechanism. And the stability of carbocations is depicted by the inductive effect and hyperconjugation, which stabilize the positive charge. As can be seen here, the inductive effect is imparted by, in case of tertiary carbocations, the 3 methyl groups in case of this tertiary carbocation, and here we have 2 methyl groups which stabilize this carbocation by inductive effect. Similarly, we have only 1 methyl group in case of primary, whereas for methyl carbocation we do not have any inductive effect which could stabilize it, hence the order of their stability and reactivity. Hyperconjugation is another factor which is responsible for the stability of these carbocations. So, in case of tertiary, we can have because of the presence of so many hydrogens in the methyl groups, 3 methyl groups present, we can have 10 resonating structures. The secondary can have 7 and the primary can have only 4 such structures, and this also indicates why and how are the carbocations attain their stability. The second step of SN1 mechanism is the faster step. Here attack of nucleophile on the planar carbocation takes place and which leads to the formation of the product. So, if we look into this example of SN1 mechanism, we will see that in the first stage, which is the slower stage, in the carbocation gets formed, which is attacked in the second stage by the nucleophile, which is a faster reaction and leads to the formation of the product and the leaving group leaves. If we look into the energy diagram, we will see the reaction coordinate clearly depicts two transition states. In the first one, the halogen atom is in the stages of leaving, there is a partial bond formation at the first stage. In the second stage, the nucleophile is trying to form a partial bond with the carbon atom, and finally, it leads to a lower energy state of the product. Hence, this is the way we can depict SN1 mechanism by the energy diagram. The stereochemistry of SN1 mechanism also shows that the intermediate in the SN1 mechanism is planar, and because carbocation is planar, so there is a possibility of attack from two sides in this. One is from the back side, as we observe in case of SN2 mechanism, and the other one is from the front side, which is because there is nothing here and the nucleophile come and attack from this side also. So, when we have attack from the front side, we observe retention of configuration. On the other hand, when the attack is from the back side, we have inversion of configuration. The net result of the stereochemistry in case of SN1 reactions is that we observe zero optical activity. This process is called racemization because we get the formation of two products, two isomers in equal amount. We have our product which is 50% in amount and we have S product which is again 50%. So, together they lead to zero optical activity. In the case of SN1 mechanism, there is another phenomena which we observe, and that is carbocation rearrangement. The carbocations may lead to 1,2 hydride or alkyl shifts within the molecule. And why does it happen? They form rearranged product if it is more stable than the starting molecule. A primary carbocation which is less stable will form a secondary or a tertiary carbocation, while a secondary carbocation will form a more stable tertiary carbocation. Let us look into the rearrangement of carbocations where 1,2 hydride shift takes place. This halide gives rise to a primary carbocation. Because this primary carbocation is not stable, so it undergoes 1,2 hydride shift and gives a more stable secondary carbocation, which reacts with the nucleophile and gives the required alcohol. And this reaction also depicts the same, but without a rearrangement of carbocation. Similarly, a primary carbocation can get converted into a secondary carbocation, which is again by a hydride shift and can form the desired alcohol by means of again SN1 mechanism. This reaction can be depicted by this particular reaction also, where the nucleophile is water and which gives rise to the product for which rearrangement has taken place. The carbocation rearrangement may take place by a 1,2 methyl shift also. The nucleophile gets attached to the carbon different from the one which had the leaving group to begin with. So, here we see that we have a primary halide and it gives rise to a primary carbocation. But because primary carbocation is not that stable, it undergoes rearrangement and gives a tertiary carbocation by means of the methyl group shift. Therefore, what you would observe is that the carbocation to which the carbon to which halogen was attached is no more the one which is substituted by the hydroxy group. So, this is what is carbocation rearrangement, which takes place to get a more stable carbocation. Let us summarize what has been dealt in today's lecture. We talked about the structure of alkyl halides because they are very important in understanding the types of reactions which these particular compounds undergo. We recapitulated some of the important terms which are used in general when we are talking about the organic reaction mechanism and organic reactions in general. The substitution reactions of alkyl halides follow two types of mechanisms, and these have been discussed in detail. The SN2 mechanism, which is a bimolecular mechanism, and SN1 mechanism, which is a unimolecular mechanism. So, we have talked about two types of mechanisms in the substitution reactions of alkyl halides. In the next lecture, we shall continue with the substitution reactions of alkyl halides, where we would talk about the factors which are responsible for SN1 and SN2 mechanism, and also we shall talk about the other important reactions of alkyl halides. Thank you.